first speaker of today is John Lakos. Now, Dr. Lakos is the author of large-scale C++ software design, serves at Bloomberg LP in New York City as a senior architect and mentor for C++ software development worldwide. He's also an active voting member of the C++ Standards Committee Library Working Group. Previously, Dr. Lakos directed the design and development of infrastructure libraries for proprietary analytic financial applications at Bear Stearns. For 12 years prior, Dr. Lakos developed large frameworks and advanced IC CAD applications at Mentor Graphics, for which he holds multiple software patents. He holds degrees in computer science, electrical engineering, and mathematics. What you may not know about John is that he's been passionate about the game of blackjack. So ever since he analyzed the mathematics of it, and he did it when he was only 14 years old. So he has been counting cards since then, and long before the MIT students depicted in the movie 21 ever took on the Las Vegas casinos. So his talk is called Value-Semantics. It ain't about the syntax. Let's have a big hand for John Lakos.
Thank you. Okay, well, welcome everybody. My name is John Lakos. I work at Bloomberg in New York. And we're going to talk about something today that is near and dear to my heart. It is not an academic exercise. It's actually very important if we're going to design software that really communicates to other people. And that's something that I find very valuable. And it's more important that other people understand what you do than you understand it by yourself. And so that's what this is about, the semantics. All right, so I want to warn you, I was asked to present this entire lecture. It can be done in an hour and a half if I'm lucky, but if there's something that's unclear and I want you guys to participate, it might go over by a few minutes. But the good news is there's a point 2/3 of the way through where you can say, okay, I've had enough. So it's going to say summary so far. I will not be offended if you want to go out and get some coffee because you will have had the complete lecture. The next two things I'm going to go over are examples, and the examples are honing your skills to see if you've learned what I hope to have taught you. They're pretty interesting, but I would understand if you get to that point and you say, you know, I really had enough, I get it, I don't need any more, I don't want to torture you. So please, as I said, I will not be offended if you want to get up and go. So with that said, here's the obligatory copyright notice. I presented this talk at ACCU in 2015, and I've updated it slightly since then, but the information is timeless, so it's going to be good 10 years from now anyway. Here's the abstract. You don't really need to read this because you're a captive audience until the summary, so you'll get this anyway. This is the outline. Normally, I talk about components, physical design, and such things, and this talk is not about physical design, but I can't help myself, so I'm going to just remind you what I'm not going to talk about first. And then I'm going to talk about what I'm going to talk about. And then I'm going to give some examples of what I just talked about. Then I'm going to conclude and tell you what I just talked about. So, the introduction. What's the problem? Large-scale C++ software design. That is what I am known for. And I talk about things like physical design in addition to logical design. And when I started talking about it, no one had a clue. Much like when I started programming, I had no idea what software was. I knew what hardware was, but what is software? Well, that was a very long time ago. And this young strapping man who said that he did something in the 80s, well, yeah, I'm a little older than he is. All right, so we have logical and physical design. Logical design is classes and functions, and that's what's taught in school, and everybody knows about that. In every language, that's common. Physical design is files and libraries. We're not talking about that today, but if we were talking about that, it would be very important for large-scale development. What we're talking about today is very important for all software development. If we were talking about physical design, we talk about a component, and a component has an implementation file. It has an interface file. This is in C or C++. In Java, it's just one thing. And it has a standalone test driver in my methodology. And that test driver is responsible for making sure that the component does what it's supposed to do. And this is our fundamental unit of design. What we're talking about today doesn't talk about physical design, but anyway, we have to figure out how to isolate and modularize our logical functionality within discrete, fine-grained physical components. That's very important, because if we don't get that right, pretty much everything else we do is useless. So we have these physical things, and they're made up of logical content, as you see up there. See if my pointer is working. Here's the logical content. And, alrighty. So, whoops, sorry about that. All right. So this compels us to delineate logical behavior precisely, which means we have to say what the software does in English. It is not good enough to write code and have the computer understand something. We need to tell the human being who's using our software what to expect, and so we have to write that in English. I can't say it enough. Contracts are in English for people. Now, the C++ standard is working on contracts that allow us to verify that the human being actually read the English contract, and in some cases, we can actually detect that the human being didn't read the contract and got it wrong. But please don't be confused. Contracts are for people, and we need to document our functionality so people know how to use it. Once we've got that, we need to put that software carefully into physical units called components and respect acyclic physical dependencies. The most important thing in software when you have large systems is to make sure that your physical dependencies are acyclic. That means you form a directed acyclic graph among your physical nodes. If you don't do that, your code will not scale, and there's no point in coming to a lecture like this because you can't do anything until you've got that right. This is just a quick picture to show you what logical relationships are. We have uses in the interface, that's the white bubble. We have uses in the implementation, that's the black bubble. And we have ISA, or public inheritance, that's the arrow. And this notation is among the bubbles, which are the logical entities. The logical entities reside in physical units called components. Those are the rectangular ones. The logical relationships imply physical dependencies. This talk is not about that, but you should know about this. And if you don't know about it, the good news is I have a book from 1996. Even better, on this particular subject, next year, early next year, I will finally have produced the next generation, which is process and architecture for large-scale C++. So that is coming out next year. Finally, I can say that because I actually finished writing it, which is something I've been working on for about 18 years. So anyway, finally, we need to share the understanding of the properties of the software that we write, and that's what we're going to talk about today, and we're going to talk about something called value types. So here is the big picture. This is a flow chart or a taxonomy of different kinds of class categories. And there aren't that many, believe it or not. You know, you don't need a lot of different things. You have some basic, a noun, a verb, that kind of thing. Well, we have about 4 categories that we talk about. And once you understand those 4, 95% of the software is taken care of, and that leaves all of the discussion to remain with the remaining 5%, perhaps, that doesn't fit into one of those categories. But if you can quickly describe to somebody 95% of the software that you're writing, that is a huge advantage. And the most important software that you write is the software that represents values, because that is the richest of all of them. And when we talk about a value type, and if we understand it, we can communicate it very quickly, very succinctly, and very accurately, and not get it wrong. And so you don't have to reinvent it. What's better is, once you know how to test such a thing, you don't have to rethink about testing because you know how to do it. It's already known. It's very easy to test things when you have done the same kind of thing over and over. I can't emphasize that enough. So these are the class categories that are important. We're going to talk about one in particular, and we're going to talk about value-semantic types. But we're going to mention the others so you know where they fit in the landscape. All right, that's my introduction to the universe, and now we're going to talk about something in Volume 2. What I'm publishing now is Volume 1. There are 3 volumes. The first one is physical design. The second one is physical architecture, I should say. The next one is design and implementation, and the third one is testing and verification. So it is a set of 3 books. They're all enormous, and it's pretty much my life's work. So I better get started because I'm 58 years old and I need to finish all of these things so that I have a legacy. So I don't want to wait another 18 years for volume 2, but I'm not going to because I wrote all 3 at once. All right, so understanding value semantics. We want to answer some key questions. And here are some of the key questions we want to answer. I put them up. If you know the answers to these, that's great. If you don't know the answers to these, hopefully by the end of this talk, you will know the answers to these. Certainly is my goal. So I give you a second to take a look and see if any of these might be challenging to answer succinctly. Okay, so getting started. Not all useful C++ classes are value types. Still, it's a very important category. We're going to begin by understanding some basic properties of value types. Then we'll contrast them with some non-value types and create a little class category hierarchy. Then we'll get to the summary, and then we're going to look at a couple of examples. So this is a true story. One of the other things that I'm talking about these days is memory allocators. And there is this belief that C++ doesn't need to worry about memory allocators. It'll just take care of, we've got a global allocator, we've got these fancy allocators and all of that, and so we don't need to worry about it. Well, back in 1997, that was 20 years ago. This is 10 years ago. I had a proposal at the Standards Committee that we adopt a certain kind of allocator in the standard. And in fact, that's the reason for this talk. That's why it got generated, because people didn't really understand what was going on, and they didn't have the vocabulary. Now, this was my second meeting, and what I was trying to do had been talked about. It made it through the first committee, but when it got to the larger committee, fear, uncertainty, and doubt, otherwise known as FUD, took over, and people got all worried and said, oh, we'll just leave it till next year. So it was not accepted at that point. So I was sitting in Kona, Hawaii, in a room with a bunch of men, no women at all, with a bunch of laptops in a U-shaped table format with no windows on the edge of this beautiful view, but you couldn't see anything. So it was just a miserable place to be with pillars, ugly stuff. And I was not happy. I will tell you, I was not happy. And people started talking about stuff. And I was wise and kept my mouth shut because anything that I said at that point would not have been taken well. And we were talking about defect issue number 684 in the wording of the working paper. What was meant by stating that 2 match results were the same? What did that mean? Now I'm sitting here and I know, but this is what happened. What do you mean the same? The 2 objects are identical, same address, same process, same time. The 2 objects are distinct. You have certain properties in common. Well, finally they figured out it turned out to be the latter. Oh, joy. Okay? So the meaning was clear. Or was it? It went on. Whatever the copy constructor does, yeah, that's it. As long as the 2 are equal. As long as they're equivalent. You know what I mean? Oh, this was torture for me. Anyway, it's purely wording. We'll let the editor handle it. I kept my mouth shut. So it's not just an editorial issue. What it means for 2 objects to be the same is an important, pervasive, and recurring concept in practical software engineering. Now remember, this was 2007, and there's a fellow named Alex Stepanov who is the inventor of STL. And in 2008, he published a very nice little book, Elements of Programming. And I carried it around in my bag for about 3 years. And I never got past halfway down the second page because it was intractable. And I would think I could understand. I had no idea what he was talking about. And then finally, about 3 years ago, I was asked by Pearson Education to interview him on the internet. So that forced me, because of his second book, to read his first one. So I photocopied it, and I sat down and I went character by character and word by word and figured out what he was saying. And wouldn't you know, what he was saying is almost identical to what I'm about to tell you today. Almost identical. And he came about it from a completely different point of view. And I think that he made the book a little bit too hard to be accessible. Many people say that. if you do have a mathematical background and you have a lot of tenacity and you're forced to do it because somebody's telling you have to interview this guy, then it might be worthwhile to read that book. If you can't quite handle that, then see this talk, because this talk is going to tell you almost everything that he talks about, and they really are about the same thing. So that's good news. It's reinforcing. Anyway, this is based on the notion of value. What do we mean by value? So what does the copy constructor do? After a copy construction, the resulting object is substitutable for the original one with respect to some criteria. What criteria? So after you copy something, is it the same object? Does it have the same address? If you change one of them, does the other one change? And so the answer is no, it's not the same object. After copy construction, you have two distinct objects at two distinct addresses. Everybody would agree with that, right? It's not Java. We don't have reference semantics. In C++, you make a copy. Most of the time, unless you're doing something unusual, you have an independent autonomous copy. So that's not it, okay? So it's not the same object. How about the same state? If two objects have the same state, does that mean they represent the same value? So here I have is that necessary? If they have identical state all the way through, there's nothing to distinguish them at all. On the other hand, what if I have two objects and they have different state? Does that mean they have different values? What do you think? Anybody think? Can I have objects with different state that represent the same value? Yes? Okay. So think about a string. We have some allocated memory. If I have two strings, then they have pointers to two different regions of memory on the heap. The state of the object is different, clearly, because they have different addresses. So what happens if we copy the address? Literally, the code won't work, because when we delete the second object, we'll corrupt the heap. So no, it's not that. So what needs to be true in order for two objects to represent the same value? What if we apply the same sequence of operations to two objects? So do they need to behave the same way in order for them to represent the same value? And we can see examples where, you know, I have an object, I reserve some capacity, and reserve some capacity, and then make a copy. Now, one question I would have is, when I copy a vector, do I copy its capacity? Yes or no? Does anybody have an idea? Is it specified in the standard whether I have to do that or not? It's not specified. I just heard that. Okay, so it's not specified. And so we really don't know, but you could say, well, but is that a general property or not? And it turns out that I can create this example here where by passing in at runtime a Boolean, I can select, based on the object's address alone, whether this prints hello or goodbye. So clearly, if I have two different objects that reside at two different addresses, they're not completely substitutable no matter what. So that notion of substitutability isn't good enough. So the behavior, if I for example, if I have two things and I copy one thing and one of them has a large capacity and one of them has a small capacity, and I now try to, let's say, push back an element, one of them will allocate memory and the other one won't. So we notice that behavior. We can observe that behavior. So it is not necessary that two objects that have the same value exhibit the same observable behavior. So we really need to have some notion of value that we can say this is what value means. And so that's what we're trying to talk about today. So what? What should be the same after copy construction? So I'm arguing it better be easy to understand, and I'm saying literally the two objects should have the same value. Now, have we made any progress? What do we mean by value? What do we mean by value? So we don't mean this. We mean something else. Now we need to talk about something that is very, very close to what Alex Stepanoff talks about in his book, and he has two books, The Elements of Programming and From Mathematics to Generic Programming. Excellent books. I do recommend that you read them. The first one is not an easy read by any stretch. The second one is more accessible, and it's also a very interesting social science and history book about mathematicians if you're into that kind of thing. But along the way, you'll learn a lot of interesting stuff that pertains to serious programming, not hacking. It's really some pretty deep stuff. But mathematical types. A mathematical type consists of a set of globally unique values, each one describable independently of any particular representation. So, for example, the integer 5. Now, for some of you, this may be hard to imagine, but the integer 5, the value 5, is unique. There's only one of them. Now, does that seem surprising? There's one integer 5. There aren't many of them. There's one. It's a Platonic ideal. There's one. And we can refer to it in many ways. We can describe it with 5 or a funny 5 or a V or in binary or the English 5 or, and of course, because I put this on a different computer, you can see that my slash is off by a little bit, so I'll have to fix that on the next iteration. But anyway, you get the idea. There are many ways to describe 5, but we're describing the same 5. Now, this is an important point, and you may think, oh, no, it's not important. Oh, yes, it is important. It's very, very important because we can't really do anything unless we accept that there is only one integer value 5. All right, there are also operations on this Platonic ideal of integers, and so we'll talk about them more later. All right, so a C++ type may or may not approximate an abstract mathematical type. And int, for example, is an approximation to an abstract mathematical type. We can't represent every integer in an int, but we can represent some of them. And we can't perform every operation on integers, but we can do some of them, okay? So an object of such C++ type represents one of a subset of globally unique values in the set of that abstract mathematical type. So in other words, a C++ object that attempts to represent a value is just another representation of that value, which is unique. The object isn't unique, but the value is unique. Okay, so now we have this class date. You know, interestingly, the standard doesn't have a date in this sense, and a date is quite difficult to write in a way that pleases everybody. We know we've tried. Howard Hinnett has tried. We're getting there. We're working on it. But you would think this is such an easy thing, we would get it right. But no, it's not that easy. In fact, there's something wrong with this. What is wrong with this? Can somebody tell me what's wrong with this class? There's something wrong with it. Anybody, be brave. And quickly, because we want to get this done on time. Raise your hand and I'll point to you. You just say it. Who wants to say something? Raise your hand. All right, you, say it. So the data member year is short, but the function returns int. Why is that a problem? Okay, so the data member can represent a smaller range than the interface type. Suppose I told you that the contract for this is we're going to represent years in the range of 1 to 9999, like the Unix calendar. And so I don't need anything more than from 1 to 9999. Now is it okay? Well, do you want me to change int year as in the interface to short? Why? Why do I want to change it? I like int. Why do I need to change it? Why do you care how I represent internally? Why don't you care about the interface, which is really where the value is presented to the user? Anyway, thank you for saying something. This is the trapping part. That's not the problem. There's another problem right here. What's the problem? Const. It's missing const. Why didn't I put const in to begin with? I didn't have room. That's the only reason. Now, if you look at the data members here, there are data members that have short year, month, day, and the size of that thing is 4 on every platform I care about. The size of this thing is 4 on every platform I care about. If I made those 3 things int, how big would it be? 12. 12 is not good. If you look at the allocator talk, you'll find out 12 is really bad compared to 4. You want locality. 12 is not locality, 4 is locality. So now you understand what's important is this, not the representation, right? So if you just learn that and nothing else, you got your money's worth. Oh, wait, you didn't pay anything. Anyway, this is important. Remember, it's what you present, not how you represent it. How you represent it is irrelevant. That's why we have encapsulation, so we can change how we represent it. Okay? Very important. All right. So these things are called salient attributes. Why are they called salient attributes? Because that's the name I came up with. Salient attributes. What are salient attributes? The documented set of observable named attributes of the type T that must respectively have referred to the same value in order for two instances of T to have referred to the same value. Truth be told, they don't need to be observable, not directly, but for the purposes of this introductory talk, let's say they're observable. Otherwise, things get harder. So we have time. Now, I'm going to tell you, there's no trick. What are the salient attributes of time? No trick this time. What are they? Somebody raise their hand and get it right for me. No? I promise, no trick. Really? Did I scare you that badly? All right. These are the salient attributes, hour, minute, seconds, and milliseconds. If two time objects have these same salient attribute values, they represent the same time value, period. Okay? All right. What would be the simplest overarching mathematical type for which std string and const char star are both approximations? This is the quiz part. Think about what is the difference between a std string and a const char star. Do they approximate the same thing? If so, what is that thing? What's interesting about an std string? It can't be null. What's interesting about a const char star? It can't have embedded nulls. But they're both approximations to something. Does anybody know what it is? Yes?
Sequence of characters.
Okay, I heard from an expert world authority that it's a sequence of characters. And of course he's correct, because he's Eric Niebler. Yes, that's correct. Sequence of characters. And it's a nullable sequence of nullable characters. That's really what it is. And each one of these two C++ types approximates it in a different way. Does that make sense? One of them is nullable, and one of them can have nullable characters, and the overarching one is a nullable sequence of nullable characters. Neither one of them implements that, but if you had a nullable std string, then you would have the full approximation that we're talking about. Make sense? Maybe? Well, in any event. So, if they both represent the same character sequence, Fred, do they represent the same value? Now this gets interesting, because is the integer 5 and the double 5, are they the same? You can have people get into like fist fights over that one. Seriously. Well, it turns out that there is a way to answer this question. If you have two types that aren't the same C++ type, but they're both approximations to the same ethereal mathematical type, then if they both refer to the same element of that ethereal type, then they represent the same value, otherwise they don't. If they don't approximate the same ethereal type, then they don't represent the same value, period. Are integers and doubles the same mathematical type? No. So what is this about 5 and 5.0 being equal? They're not the same, but for some notion, they're equivalent. For some notion. I don't know what that is, but for some notion, they're equivalent. But they're not the same. So you have equal, you have equivalent, and you have the same. What's the difference? When two things are equal, there are two things. When they're equivalent, there are two things. When they're the same, how many things are there? One. I had an example in the real world. There's a mother-daughter, and they had a pair of rings. And the mother said, "We have the same ring." And I said, "No, you don't. They're not even the same size. What is wrong with you?" They're two separate objects. They're not the same. Well, that didn't go over very well. She's a psychologist, and I got told that I need to improve my personal skills. All right. This is important, so I took a little extra time. What about integers modulo 5? Are they the same as integers? If I have an integer modulo 5 and I have an integer, are they part of the same algebra? If I take 3 plus 3 modulo 5, what is it? 1. If I have 3 plus 3, it's... So something's different. So the mathematical algebra of mod 5 and the mathematical algebra of not mod 5 are not the same. And yet 2 somehow is equivalent to 2 somehow. But how? I don't know. Anyway, an interpretation of a subset of instance state. So the value of the salient attributes and not the instance state, not how we represent it, is what we're talking about when we're talking about value. And we can compose things. So here I have a point, and I have x and y. And here I have a box, and it has a point for the origin, and then it has a length and a width. And notice that I have salient attributes, and one of the salient attributes is described by an aggregate of fundamental types, which themselves are value types. So how about vector? Here's another test. What are the salient attributes of a vector? The size? Is that salient? Do we need to know, if we're talking about a sequence of integers, do we need to know how many integers there are to talk about the value? Let's hope so. Because if I have a sequence of 3 integers and a sequence of 2 integers, do they represent the same thing? Hell no. So they better have the same cardinality. What about the respective values of the elements? Should they be the same? So the respective elements should represent the same value. They're not equal. They represent the same value. That's it. Okay. So if the sizes are the same and the respective elements represent the same value, then the two vectors represent the same value because there is a notion of a mathematical sequence, and a vector approximates a mathematical sequence. And if it's a vector of int, it approximates a mathematical sequence of ints. That's it. Okay. How about capacity? Is that salient? Yes or no? Somebody who's brave and really willing to stand up for what they believe. Yes or no? Raise your hand. Who said no? Raise your hand. I want to say, who? What? No one's reading. There you are. Now say it. No. Yes, you're right. So how do we know that capacity is not salient? How on earth would we know that? Say it louder. It's part of the implementation, but I can get it. I can ask a vector for its capacity, right? Okay, so I'm going to repeat what was said. In the standard, you can compare two vectors, and they can have different capacities, and yet the operator double equals, the way it happens to be implemented, says they still represent the same value because that's what it... Okay, and it's also that it's the only reasonable definition. I'm not arguing, I'm just saying how are we supposed to know? Salient attributes are part of a logical design. It should be natural and intuitive, right? Shouldn't be crazy, and must be documented. You got to say what's salient. It's not something you were born with, right? Oh, I knew that std vector has these salient attributes and this one isn't salient. And you might guess, but it has to be stated somewhere. Why is value important? Well, it turns out that it's important for a reason, IPC. And when I was young and just started working in CAD, we didn't have a lot of IPC. I thought my computer was my own island and I didn't need to talk to anybody else. So why would I ever have to externalize something outside of my computer? All right, well, so we have an abstract date type. Has an infinite set of values. Here they are. That's the infinite set. Notice it goes off the screen because it's infinite. And then I have a C++ date class, and it can represent a subset of those values, and every object, in our case, does represent one of those values because our date class has as an invariant that it represents a date. We don't have date classes that don't represent a date. And that's another discussion that we could have. Well, why not? Well, if it doesn't represent a date, then we have to worry about whether we can talk to it or not. And so, anyway, they represent a date. And by represent, I mean that those objects are not dates. They represent a date value. And that's what those lines indicate. Now, if I have a database and I want to save those dates to the database, how many people think they're represented the same way as they are internally in a C++ date class? Anybody? Anybody think they might be represented differently? Yes. How might they be represented differently? Who knows, right? Anyway, could be completely different. But they still represent the same value. These things in the database refer to the same value. They're not equivalent. They're not equal. They refer to the same. You have a new appreciation. You had equivalent, you have equal, and you have the same. That's identity. Values have identity. All right, now you have Java. And somebody might want to write something in Java and then read the database. And when they do that, the Java objects will refer to the same value. Now, how is this different from photocopying something and photocopying it and photocopying it and photocopying it? After 100 photocopies, it gets blurry, right? Because there's this analog attenuation of signal. But that doesn't happen here because it's the same thing each time. There's no loss. It's lossless. Every single one is referring to the same thing. You could do this 1 trillion times and it would be the same thing again and again and again. It's lossless. You need to start thinking this way. It's not just an academic exercise. We need to be able to communicate value to everyone, and we need them to understand what value means. What types are naturally value types? Not everyone is, right? So what is this? It's a flashlight. Look at that. What's its state right now? Off. Now. Come on, loud. Okay. What's its value? All right, there's no notion of value per se that we could count on. So not every stateful object has an obvious value. Here are some stateful objects that don't have an obvious definition of value. What would it mean to copy construct a thread pool? What would that mean? Does anybody feel, if your boss told you, I want you to make sure that that thread pool has a copy constructor, what would you tell your boss? All right, that's another question. A scoped guard is the quintessential non-value type. What does a scoped guard do? It keeps track of a resource. It doesn't communicate anything. It does something, right? It gets rid of the resource when it goes out of scope. Here's some more things. Do any of these things have a value? Do they try to represent a value, or do they do things? Remember when I told you we have like nouns and verbs? The English language doesn't have all that many parts of speech. C++ software doesn't have all that many parts of speech, not in the real world. And as I said, the last 5% is everything else. But in the real world, if you could just get the 4 basic categories down, 95% of your work would be already done before you started. You know how to test it, you know how to think about it, you know how to document it, you know how to teach it. It's all good. That last 5% we leave for Eric. All right. Suppose we have a thread-safe queue used for inter-task communication. Is it a value type? Now, this is a hard question. This is not an easy question. Should this object support value-semantic syntax? I have a thread. I have a queue, and it's intended to communicate, to be used to communicate across threads with appropriate serialization. Should it have a notion of equality comparison? Should it have copy construction? Should it have assignment? Or not? What do you think? What's the purpose of the queue? Is it to represent a value, or is it supposed to do something? You said both. Who said both? All right, so now here's the thing. You have to make an engineering decision. It certainly is supposed to do something, but is it also supposed to represent a value? You have to think about that, because if you make it represent a value, somebody will use it to represent a value, even though there's something much better to use to represent a value than a thread-safe queue. So anyway, think about that one. We refer to stateful objects that do not represent a value as mechanisms. So in this chart, we have these class categories, and mechanisms are over here. Mechanisms are not as rich a taxonomy as value types. There's not a lot you can say about a mechanism other than it's a stateful object. It may or may not allocate memory. We don't know. It does something, but it doesn't try to represent a value. So my object, here's an object, stateless object, stateful object. Stateless objects could be a utility, could be a functor, could be a metafunction. Let's take a look at a utility. Now this always gets people going. I have a struct, dateutil. And in it I have static methods. And people say, John, what are you, from the 90s? We have namespaces, we have all these wonderful things. Why are you doing this? Well, I'm doing this because it's the right thing to do. Because I don't want ADL. I don't want people to spread this all over creation. I want this to be a node in my physical hierarchy. And I want it to be very clear that these are functions scoped within a node, because individual free functions floating around in a namespace that could span multiple components is exactly not what I want to do when I'm designing code. I want to be able to do this. There are about 7 reasons why I do this, and in fact, static was deprecated and then undeprecated. So I'm very happy that this continues to be a reasonable way to do things. Nonetheless, one of our class categories is a utility struct that has static methods. And this would be the analog to algorithms in the sense of the STL. These are not templates. These are functions that work on things. It's, as an aside, when you have something like a string class, you want it to be sufficient, complete, and minimal for what you're trying to do. And every application on it that does not require private access should not be part of the string. It should be part of a utility struct. Or if it's a templatized utility struct. Or if it's using iterators or ranges or whatever magic is going on. But in the real world, there are a lot of things that are just, I need a function that works on a value type. So tangent of something, we got a bunch of functions. Tangent, sine, cosine. It's not double dot tangent. It's tangent of double. That's just the way it's always been, and I'm fine with that. And I think it's okay to have, next Thursday of date and get back whatever that is. All right. Utilities are an important class category. You have value types and you have the functions that work on the value type. So right there, that's huge. Sufficient, minimal, complete value types, and then stuff that works on them. You can have many different physical entities that operate on a value type. You want the value type to be stable. Sits low in the hierarchy, doesn't depend on a lot of heavyweight things, doesn't depend on a database, doesn't depend on it. Just its purpose in life is to represent a value. If you get that right, you're well along. As soon as you say, well, this date class knows the operating system can figure out what today is. Bzz. No, that's not what you want to do. All right, that's what a utility is, so that's over there. Does it have a value? So it's either a mechanism or a value. If it's yes, it's a value type. If it's no, it's a mechanism. If we look on the chart, yes, value semantic type, no, mechanism. So here's the big picture again. Those yellow things are exemplars. If you were to go look on GitHub, Bloomberg BDE, you could actually find some of these things. It's open sourced, so you can look at it. There's also the fourth one, which is a pure abstract interface, also known as a protocol. What does it mean for two abstract types to compare equal? Does anybody have an idea what that means? Suppose I have fruit, and I want to compare apples and oranges. What does it mean? So the idea here is it's not a very meaningful thing to do, because what we're really talking about is non-virtual things. Concrete things are for variation in value, and abstract things are for variation in behavior. And Cargill got this right a long time ago in his programming style book. This is circa 1992. I remember reading these early books. I learned some really good stuff from Myers, Murray, and Cargill back in the early 90s. What syntax should value types have? What do you think? Value semantic type defines the following. Default constructor, which not necessarily is initialized, but does have an initializer. Okay? Copy construction, destruction, copy assignment, swap sometimes. This is called a regular type. This is what Alex Stepanov calls a regular type. It's got certain syntax, and it also has certain semantics that are very illuminating. And his definition of the syntax is very rigorous. I mean, the semantics is very rigorous. You can't have just any old operator double equals. If you have an operator double equals, it definitely behaves a certain way. So here's operator double equals. These things have to be true. Everybody knows that. We would want this to be true, otherwise we'd be very confused. Here's another one. Do you know what I'm talking about here? If A equal D compiles, then D equal A compiles too. That's a good thing, right? You would be surprised if one worked and the other didn't, right? This talk is not about syntax, but I couldn't help myself. It's amazing. There's always one person or two in the audience, this audience, maybe three, because it's a big audience, that didn't know this. So I have to say it, even though I say it all the time. What am I talking about? Well, suppose I have a class and it has a member operator double equals. And then I have a class that knows how to convert itself to this type, T. And I write this code in function f, and it works. And then I try to write it the other way around, and it doesn't work. Well, this violates the element of least surprise. People don't like that. So how do I fix this? This is a bad idea. Member operator double equals is just a bad idea. If you do it, stop it. Make it a free operator. Then everything works. This is proper. You say, yeah, John, I understand. But there are times when I can do it, right? I can do it like with a string class. Yeah, I'll make the general one like that, and I'll make the one that has the const char star on the left. So I was just saying, well, of course I'm going to have the general equal for the class, and then I'm going to have the one where the char star is on the left because we know we can't make it work. But certainly I could put the one with the char star on the right inside. How could that matter? Well, turns out I'm very clever with these things, and I can construct a foo that knows how to convert itself to a string, and I can create a bar that knows how to convert itself to a const char star, and then I can create this wonderful piece of syntax, and then reverse it, and it doesn't work. Oops. So the answer is don't try to be too clever, because I'm also clever, and I can get around it. That's what I do. So we'll just make them all free, and then we won't have to worry about it. So the right answer is make your double equals free. It's proper. It's the right thing to do. They should always be free. All of these guys should always be free, but not these guys. There's certain criteria for when you want to make things free and when you want to make things members. That's not the purpose of this talk. It is an interesting exercise. C does it one way. C++ does it another way. And objects do it one way, and fundamental types do it another way. And to say do as the ints do is not enough. But that's another story. It's not about syntax. What semantics should value types operations have. So the salient attributes of a type T are the documented set of named attributes whose respective values for a given instance of T derive from the same physical state of derive from the physical state of only that instance, nothing else, and they must respectively have or refer to the same value in order for the two objects to have the same value as a whole. So we could try to do something with copy construction, and of course, we have to copy all of the representation of the salient attributes or things wouldn't work. But what about capacity? We don't know if that has to be copied. It may or may not be copied. It's up to the implementation. We can't look at the implementation of a copy constructor to know what's salient. It doesn't work. We don't have enough information. So the copy constructor can't help us. What about compare equal? Can that help us? So the associated homogeneous free operator equal for a type provides an operational definition of sameness. You can look at the code and you can know the answer. And then you can look at the documentation for that function and it will tell you the specification. So the specification for operator double equals is the operational definition in words of value. Okay? This is where you look when you want to know what value means in a value type. So value-semantic objects share many properties. Each of these properties has to be objectively verifiable irrespective of the intended application domain, which means we don't do crazy things like saying this integer reduces somehow. It does, or this fraction reduces, because as soon as you start to introduce those kinds of things, craziness ensues. Now there's another thing. What about attributes that are orthogonal to value? Should they be copied? So here I have NMOS and CMOS registers. Do people have an idea that NMOS is an older technology, dissipates a lot of power? CMOS is a newer technology, and by newer I mean it's only 30 years old. That's the era that I was dealing with these things. Anyway, so if I have an NMOS register and a CMOS register, they can both represent an 8-bit value, but they're different technologies. So these technologies have nothing to do with value. They're how I represent things. Now, if I do an assignment, these are not equal. If I do the assignment, look what happens. Now they're equal. They represent the same value. But now imagine if assignment did something like this. What kind of world would we live in? So that is not what assignment does. Assignment does not change the type of an object. We have to keep that in mind. And so if you have a virtual table pointer, it would be really rude to change it through assignment, wouldn't it? That would be nasty. Same with an allocator, by the way. Same idea. You set up an allocator, you've created something, it's a certain technology, and then somebody assigns something and it changes the technology? I don't think so. So don't do that. Choosing what's salient will affect our ability to test things thoroughly. It'll also affect the sanity of our code. All right, suppose we have value-semantic type A, B, and C are objects of the type D is of some other type. So if A equals B, then if implies that A and B have the same value, assuming operator double equals exists. And it's possible that it won't. Why not? Sometimes a value-semantic type is almost regular. We'll find out why shortly. All right. The value of A is independent of any external object or state. Any change to A must be accomplished via the public interface of the object. So now imagine we have something that refers to another autonomous object, say a record. It's got a pointer. So the value actually incorporates an address. Now we're not talking about this in this talk, but my talks always talk about stuff we don't talk about, so I have to talk about this. Here I have an example of an element pointer referring to a record. It doesn't own the record, it just refers to it. So operator W, two element pointer objects have the same value if they, 1, refer to the same record object in the current process, 2, have the same element index. So, are these two record objects equal? Does it make sense to talk about that? The answer is no. The record object might not be value semantic at all. It could be a lump of coal, for all I care. What's important is that it has the same address. So all of these things refer to the same record object. So objects 1, 2, and 3 are candidates for representing the same value. And now there's something else in them, which is the index, that refers to the element within the value. So objects 2 and 3 represent the same value. This value is a different kind of value, though. It's not representing a mathematical type. It's relevant only within the current process. What's good about this is if the record object A changes, they're still the same because they're referring to the address. They're not referring to different objects. Otherwise, they might be the same today and somebody comes along and changes one of the record objects and now they're not the same. But the record objects don't even have a notion of value maybe, so the whole thing makes no sense. This is called in-core value semantics. It's not full value semantics. It's not what we're talking about today because we're talking about approximating ethereal mathematical types, and this is just an expedient of programming sometimes. So you can pretty much forget about that. All right, a C++ type that properly represents a subset of the values of an abstract mathematical type is said to have value semantics. Properly, what do we mean by that? Recall the two distinct objects A and B of type T that have the same value might not exhibit the same observable behavior. E.g., one might allocate and one might not. But that's not what we're talking about when we're talking about value. If two objects initially have the same value, represent the same value, and we apply the same operation to both, then unless something blows up, they will again have the same value, otherwise they never did. That's what you need to know. If that's not true, your code is broken. Okay. This is the subtle essential property of value, and deciding what is not salient is surprisingly important. And there's a lot more to this story. Now, this is not a test driver. This is saying if I have two things that are equal and I apply the same salient operation to both, they will continue to have the same value provided they are the same C++ type. Suppose I have a homegrown ordered set, and here it is. It's called ordered set. And I have a way of constructing it so that its collating sequence is increasing or decreasing. Now, suppose the two sets are constructed differently. Okay, should two empty objects be considered equal? Who is sure they know the answer? Raise your hand. Come on. Should be obvious by now. I already told you everything you need to know. What happens in C++ right now if I have two different types and I try to compare them? Go ahead. What this gentleman did is just get the right answer and explain why. Let me do it for everyone else. Suppose I have two empty sets. They don't have any elements, and we say, yeah, they're the same. And then I put the number 5 in one of them and the other one. Well, they both have 5, so they're still the same. Then I put 6 in. And now one of them is 6, 5, and one is 5, 6. Remember, they're ordered sets. Well, if they're ordered sets, 5, 6, and 6, 5 are not the same. Therefore, I found a distinguishing sequence. Therefore, they never were the same. Therefore, this entire thing makes no sense. Fortunately, the way templates work, if you try to do that with two different types, you can't compare them. It won't compile, and that's actually a good thing. So this doesn't come up unless you get too clever. And then when you get too clever, you need to know not to be so clever. Just saying. All right, so the answer is no. These two objects of the same type that were created differently do not represent the same value because there's a distinguishing sequence. Okay? So remember, these are salient operations. When unordered container was changed from unordered, or unordered set was changed from unordered, unordered map was changed from hash map, or unordered set was changed from hash set. People really thought that the data structure had to talk about hashing and really had to talk about getting the nth element out of some bucket. That is not what an unordered set is. An unordered set has a notion of, are you a member, add a member, those kinds of things. It has nothing to do with the hash part. That's not salient. And so there are a lot of operations on unordered set and unordered map that you can do to distinguish them, but that does not mean that they don't represent the same value, and iteration order may or may not be salient. If you have an unordered container, iteration order is not salient. If you have an ordered container, iteration order is salient. Things like that. Okay. What makes two unordered containers represent the same value? Now, think about this. Suppose I have two unordered multi-sets. So I have 2 bags of candy. How do I decide whether those 2 bags of candy have the same value? And I promise you 2 5-year-olds can figure it out. What do? They dump the candy out, and they put the candy in one-to-one correspondence in a line. And if it's possible, then they represent the same value. Otherwise, they don't. Right? That's as simple as that. That's what's important. That's what's salient. All right. Now, remember, it's the same type. If I do if I do the same operation to both, what if they're different types? So I make one of them a short. Is it true anymore? No, because if I do it enough, something may overflow. It's undefined behavior. So what I'm talking about primarily is for objects of the same C++ type. How do we design proper value types? So now we've got this notion of numerator and denominator. All right. Should that be the salient thing? I've got operator double equals, blah, 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 blah. Okay, 2 rational objects have the same value if the ratio of the values of numerator and denominator for LHS is the same as for RHS. That's a possible definition. So 1/2 and 2/4, 1 over 0, 2 over 0. All right, that doesn't matter. We can just ignore that. How about this? Do these represent the same value? And then what about this? Now, it turns out that if we do the same operation to both, one of them will overflow and one won't. So now we get into trouble about representation. So this is not a good definition in practice. And so what we're going to do is say, either we represent things in canonical form or we don't expose the individual pieces. So if I want to say that 200 over 100 is the same as 2 over 1, then I don't want to show the numerator and denominator separately. That's a suggestion. 2 objects have the same value, then the values of each observable attribute that contribute to value should respectively compare equal. That's a suggestion. When should we omit valid values? So we're going to talk about graphs. So this harkens back to physical design. We have this nice picture, and you'll notice that it has all kinds of implied cyclic dependencies among the entities. And we say, well, we can use some levelization techniques from Lakos 96 or Lakos 2018. We can use these things. We can make it a little simpler. Or for the purposes of exposition, we're going to make it really stupid simple. We have a graph, and we have nodes, and the edges are just relationships among the nodes. So we don't have an edge object. So here's a graph, has a bunch of nodes. We have a notion of we can get the node that's adjacent by giving it the index of 0 through 4. And there's some const issues here because I ran out of room again. Const is a real pain for slides. So this particular index is node 2, and it has 2 adjacent nodes, and those adjacent nodes are 0 and 4, and the first one I get by putting in 0, and here's my graph, and I have an operator double equals. 2 graph objects have the same value if, what are the salient attributes of a graph? Somebody tell me. What do I need to know for 2 graphs to have the same value? They have to have the same edges. So think about what you just said. They have the same edges? What does that mean? The adjacency of the nodes, something like that. Do they have to have the same number of nodes? Or can they have different numbers of nodes? For 2 graphs to have the same value. Same number of nodes? Okay, good. Do they have to have the same number of edges? Same number of edges. How about number of nodes adjacent to each node? Okay, so that's true. Well, if that's true, then certainly I don't need number of edges because I have, per node, I have the same number of edges, right? That's good. What about specific node adjacent to each node? Right? It's not just any old node, it's those specific nodes. Well, if they're the specific nodes, then I don't need the other one, right? So, two graph objects have the same value if they have the same number of nodes n, and for each node I, 0 less than I less than n, the nodes adjacent to node I and in LHS have the same indices as those of the nodes adjacent to node I in RHS. That true? So here we go, adjacent nodes. Is edge order important? In other words, if I iterate over the edges for a node, do they have to come out in the same order in order for the two graphs to represent the same value? If you think about one way of representing edges, it could be an adjacency matrix. And in an adjacency matrix, there is no order. It's just a matrix. So you have to decide, is the order of the edges salient or not? What do you think? Should it be or not? No. All right, we could maintain them in sorted order and then it would not be a problem. So if we maintain them in sorted order, or if we represent it as an adjacency matrix, then we have this, operator double equals ordered edges, unordered edges. Now, if they're unordered edges, in practice, the big O is going to be n plus e squared, because we're going to use a hash table to look it up. And in the ordered edges, it's going to be n plus e, because we've got it already organized, and we can just traverse it. Now, this is not the best big O case. We could actually make it this way, but that would be dumb from a expected case runtime. All right. So as I said, just got my note that I have 15 minutes. Well, I am going to go over, so I'm warning you, almost getting to the point where you're going to, if you're done, you can go, but I'm going to go on a little bit longer because I do want to get through this because I was told to, so I'm going to do it. It's not all or nothing. It turns out we don't need to have everything in order for something to be value semantic. It turns out that unordered sets is a value semantic type, but until I threw a fit in 2010, it did not have an operator double equals. And there was some discussion about whether unordered set should make the order of iteration salient, and the argument for it was, well, it'll be faster if we make it salient. And it's like, yeah, but it'll be wrong. And they're like, well, but it'll be faster. Anyway, I am very stubborn and annoying and persistent, and I got my way. So we do have the right semantic, and it's very fast because there's a fellow named Pablo Halpern who came up with an algorithm that in the normal case where things happen to be in the right order because they were copy constructed or assigned, you get it in the number of operations that correspond to the number of elements. So not only linear, but linear with a constant of 1. It doesn't get much better than that. All right. So if you don't have an operator double equals, it's not regular. But it's an excellent starting point. So if I have something that's not regular, but I say it's regular, but it doesn't have an operator double equals, well, it's like saying, okay, I have a zebra, but it doesn't have stripes. Okay, it's a horse. Got it. So the name for this is semi-regular. If it doesn't have an operator double equals, but everything else is working, it's semi-regular. And that's Stepanoff's terminology, and so we'll go with that. What are the salient attributes of a graph? Number of nodes, specific nodes adjacent to each node, not the adjacent node order. We're not going to count that. What about node indices? Do I have, when I iterate over the nodes in two graphs, do the nodes have to come out in the same order, or can they come out in different orders? What do you think? Different orders. Okay, so your boss tells you, well, if you think it's different orders, then different orders. But I want to make sure that we can compare the two, so I want an operator double equals, and of course not equals as well. Now where are you? You're in deep trouble. You've dug yourself a hole that you cannot extricate yourself from. So be careful before you promise what you can't deliver. So, two graph objects have the same value if they have the same number of nodes, and there exists a renumbering of the nodes in RHS such that for each node index I, 0 less than I less than n, the node adjacent to node I in LHS, the node I in LHS have the same indices as those of the nodes adjacent to node I in RHS. All right, so here's a graph. This is node index 3. Here's another graph. It's had the nodes renumbered. And are these the same? They sure look the same. If you look at them, they're the same. But if you want to try to deal with them from a computer point of view, might be problematic. What if I kind of distort the picture a little bit? Turns out that these graphs have the same topology, but how am I going to write something that's going to tell the difference? How hard is it to do that? Anybody know how hard it is? No? All right. Should operator double equal mean isomorphic? We said the same. They're not the same. Isomorphic. Okay, well, we should talk about what that means. So this is graph isomorphism. How hard is graph isomorphism? Somebody said NP hard. Well, it's known to be in NP and co-NP. It's known, so it's no harder than that. It's not known to be NP complete. So it might not be that hard. But it's also not known to be in polynomial time. So it's somewhere in between. But the bottom line is it's hard. And when something that's hard, they didn't even want to have something that in the worst case was quadratic for operator double equals for hash tables, which was nuts. But they're not going for exponential. That's not happening. So here's a case where we just can't do it. It's not possible. And if it's not possible and you have to do it, you're in a bad situation. So we're not going to do them. We're going to say instead that the ordered sequence of nodes adjacent to node I in LHS has the same value as the one for node I in RHS. What we're saying is if you want to implement operator double equals, you have to compromise on your notion of value. Otherwise, you have to leave it out. You have to say, I can't do that. So number of nodes, specific nodes adjacent, and as a practical matter, the numbering of the nodes, or leave it out. And perhaps provide a utility function that says these two graphs are isomorphic. That's the right answer. Don't try to do it with operator double equals. Operator double equals has a meaning that is independent of domain. You either get it right or you go home and you do something else. Okay. Why would we ever omit the valid value syntax when there is only one obvious notion of value? When we cannot do it efficiently, when it's not possible, or when it's off message, like the queue. You remember the queue that was working with two separate threads trying to provide a service, and now we're saying we're going to use it as a value type? Maybe you just don't do that so you don't confuse people. This is the summary so far part. I'm a little behind time, so I am going to go over. So I warn you, if you've had enough of this, when I finish this summary, leave. I'm going to ask a couple of questions, and then I'm going to finish this. It's going to go on for a little while, probably about 15 more minutes. So, when selecting salient attributes, avoid subjective domain-specific interpretation. Fractions may be equivalent, but not the same. Graphs may be isomorphic, yet distinct. Triangles may be similar and still different. Don't editorialize on equality. Relegate any subjective interpretations of equality to named functions, ideally in higher level components. Not the same component, this is just a picture. You would put them in different components because they pertain to different types. Okay? Yes, I'm using static methods of a struct because I can. And it's fine. And it's the right answer. And for people who don't think it's the right answer, you can heckle me all day long. Please buy my book. It'll explain to you why you're just wrong. All right. Saying what we mean notice I'm shy about my opinions. Saying what we mean facilitates understanding. I just told you what I meant, which is that static, struct, good. Objects are the same. Objects are identical. Objects are equal. Objects are equivalent. This is all crap. Don't say those words. Never, ever again use the word equal in documentation. Please. At least not for, you say they have the same value or they don't have the same value. We don't need four of them. They have the same value, they have different values. They don't have different values. There's only, they either are the same or they're not the same. That's it. Okay, be precise. Say exactly what must be the same. Objects are the same, objects are identical. That's identity. Aliases refer to the same object. Objects are the same value. Objects have the same value. Objects refer to the same value. Objects represent the same value. Same, not equal, same. Objects are the same, objects are equal, equality. Objects compare equal. When you're trying to talk about operators in a class, you say these objects compare equal when they have the same value. That's how you say it. Homogeneous operator double equal returns true. For value-semantic objects, that means they have the same value. Objects have the same equivalent. In separate named functions, fractions are equivalent, graphs are isomorphic, triangles are similar. Okay? So I'm going to stop here and take a couple of questions. I'm serious. If you feel like you've had enough of this, go away. Anybody have any questions? Because I'm going to give 2 examples. They're kind of interesting. They're going to apply what we've learned here. Questions? Seriously, if you want to go, please do. I'm not offended. Because we're almost out of time anyway. Literally, I have only 5 minutes left. And this is going to go on for a few minutes longer. Maybe 15. Any questions? No questions? It's all good? All right. Well, I want to give people a chance to do this. This is the hardcore stuff. Now we're going to get to the real deal. So it's good that we have the tenacious ones to stay. But honestly, I've said everything that I need to say, so you have all the equipment that you need to do what I'm about to talk about. This is just practice. All right. So 2 important instructional case studies. Regular expressions. So what is a regular expression? Why create a separate class for it? Should it represent a value? How should its value be defined? Should such a class be regular in the sense of Stepanov? So let's start with what are regular expressions? Regular expression describes a language that can be accepted by a finite state machine. For example, 1 plus 0 describes binary numbers. 1 or 0 quantity plus. 1 or more of those. Okay? Next, why create a separate class for it? Regular expression class imbued with the value of a regular expression can be used to determine whether or not arbitrary string tokens are members of the same language that the regular expression value denotes. So we have this notion of a language. That's what a regular expression object describes. So here's a plausible interface. We have a isValid function for the regular expression. We have some constructors, and so we can create an empty language that accepts nothing. Why we would do that, who knows? We can provide a string to initialize it. We can copy construct one if it's a value type, and we can destroy it. So those are the creators. You'll notice that when I have any type, I have my static methods, I have my creators, I have my manipulators, I have my accessors, and then I have my free operators below. So here are the manipulators. I can assign the value. I can, whatever the value is, I can set the value. Again, what is the value? And I can set the value if it's valid. And you might say, well, why do I need both of these? And the answer is, in general, if you have a complex constrained type, you're going to want to be able to check it to make sure that when you assign it a value, that you have a valid value. You don't need to do that for simple things. If you have a single scalar, if you have a range, it's not important. But if you have something like a date and you supply year, month, day, there are times when you don't know if year, month, day is a valid date, and you want to be able to assign it only if it's valid. You want to check status. Then there are times when you know it's valid and you absolutely do not want to check status. And in fact, in certain build modes, you want the thing to tell you what's wrong with you. That's not a valid date, and you said it was, so you're wrong, so I'm going to report you. And that's a good thing, and that's called defensive programming. And that's another topic as well. Very important, but that's what the standard is going to have in C++ 20 if I have my way, hopefully. All right. And then there's this last one that's called isMember. And basically it takes a token and it says, is this string a member of the language described by the regular expression? Could have been called except or matching. So which operations are salient? Anybody want to guess which of these operations are salient? Thoughts? isMember. Anything else? Just one, isMember. Very good. See, the people who stayed are paying attention. That's awesome. Let's think about that. The only thing that matters here, really, the only thing that's part of an abstract mathematical type is to ask the question, is this string part of this? And everything else that you see there is just mechanism and noise and C++ and ick. There's one good thing, and the one good thing is this string a member of this language? Okay. Should this object represent a value? So, what do you think? It's pretty obvious what it's going to be, because why would I be talking about it? Yes? It's a functor object that stores the parameter of the function. I'm not sure what you mean by that. Can you explain? Okay, so I'm being told it's not a value per se. It represents a value because it represents a whole language. So let me ask you a question. Is the subset of strings that is part of a named language a value? I have an infinite set, and then I have a particular subset of that infinite set that corresponds to something. Let's say English. Is English a value? Oh, is Polish a value? Is German a value? So I'm going to say yes. Are binary numbers a value? Yes. Right? How about legal Turing machines? Is that a value? Okay, so it's a value. The notion of the value is the language it represents, so I claim yes. There's a value there. Now, people will vary in how much they want to, how far they want to go to represent something that's a value. Some people will tell you that in functional language, the function itself is a value. But for sure, if I have an infinite set of strings and I have a infinite subset that conforms to some rule, that's a value. That's different from some other language that accepts some different set of strings. So I'm going to say yes. All right. How should value be defined? Should it be the string used to create it or the language it accepts? Language. Why not the string? So I could represent the same language with different strings, right? And who cares? What I care about is, does it accept the same language or not? So why would I care about what string I use to initialize it? Good. Note there's no accessor for the strings. In my opinion, the correct answer is 2. And actually, the reason there's no accessor is I don't care how it was initialized. What I care about is what its value is. How would I get the value of a regular expression out of a regular expression engine? Notice it's not accessible. It's a salient attribute that's not accessible. See, this is the advanced part of the talk. It's salient, but it's not observable. Not easily, but it's there. So what makes a regular expression value special, distinct from other used to create it, is the language value. So I could have 2 regular expressions that represent the same language. I don't care. Ideally, they'll be the same state machine, and so on. Ideally. Had we provided such an accessor, it would not be considered salient. So we could have gotten the thing we used, but it's just a piece of noise. Again, it's not relevant. It's like capacity. or iteration order for an unordered container. Perhaps we could have named it something different, like language. All right, and finally, should such a class be regular? I.e., should our regular expression class support the value semantic syntax of a regular class? What do you think? No. I can't provide equality. How expensive would operator double equals be to implement? Infinity. Infinity. Wow. Never heard that before. All right. All right. So in honor of this very important question, I'd like everybody to stand up. So stand up. Stand up. We need some respect here. You'll remember this, believe me. We're all standing? Okie dokie. So now here's how it's going to work. When I put something on the screen that's too big, bigger than infinity, when it's too big, I want you to sit down. So far I've put O of 1. So if O of 1 is too big, you should sit down. Don't sit down. Okay. Log n. Now, if you think it can be done in O of 1, sit down. Does anybody think it can be done in O of 1? No? Okay. So you see how this works. How about square root of n? That means if it can be done in log n, sit down. How about n? That means if it can be done in square root of n, sit down. How about now? Can it be done in linear time? Who wants to sit down? No one? Okay. If you think it can be done in linear time, this is your last chance to sit down. You're all standing. All right. Not n log n? Sit down. Someone sat down. All right. Can it be done in n square root of n? Who's going to sit down? All right. Who can do it in quadratic time? You're going to show me that one, right? All right. How about n squared log n? All right. Who can do it in polynomial time? Certainly someone can do it in polynomial time, right? No? Yes? Ooh, you thought about it. Okay, is it in NP? All right, is it NP complete? P space? P space complete? Undecidable. It's P space complete. All right, so this is hard. This is like seriously hard. This is how hard it is. I had to use strange letters. What does it mean? That's what it means. In essence, it's not, as far as we know, it takes exponential time and polynomial space, and it's not happening. So we're not going to do that. So the bottom line, P space complete, and clearly no equality comparison operators. And so if you wanted to ask the question, it would be a separate function, and on the function it would say, by the way, if you call this function with more than about 3 characters, you can go home. All right. Copy construction and assignment aren't a problem. Stepanov requires that for regular classes, quality comparison must be done in linear time with respect to the real estate that includes the footprint and all owned memory of the object. I do not require that. I am okay with an operator double equals that takes O of n squared in the worst case. And that's about the extent to which we disagree. But his requirement is a regular type has the semantics that all operations are linear time. He's allowed. He's retired too. Okay, discussion on this one. Okay. Okay. No, that's okay. Well, you mean, so I shouldn't do the second example, or I should?
What is the room saying? I'm afraid we only have 10 minutes left before the next.
I'll do it real quick. I'll try to do it. Okay, so what's a priority queue? Priority queue is a generic container that provides constant time access to top priority elements. The top priority element defined by user supplied priority function or functor. So the operations are top, push, and pop. And these are the salient operations. Here's an example of an element that we might put in a priority queue, and it's just a labeled point, and it gives you distances in terms of a Manhattan distance. So this is how a priority queue works, and I'll just go through this really quickly. Each element is labeled with its calculated priority. Each distance color represents an element having a distinct value. And so if I assert top 2, you see, yes, different priorities, different values, different priorities, different values, same priority, different values, same priority, same value, and same priority, different values. So if we push 2, we put it at the end, and then we bubble it up, and you can see how that works. Okay, and then it doesn't go any further. And then if we want to do a pop, so I pop that, I take the one off the end, I put it there, and then it has to bubble down in the same way, and you'll see that it bubbles down like this. And then it stops. And that's it. So that's how a priority queue works. So if you never knew how a priority queue worked, now you do. So why create a separate class for it? Because it's a cool data structure, so I'll put this up. Should it represent a value? Obviously, because I wouldn't have it up if it didn't. And assuming, of course, that a queue element type also has value semantics. If it doesn't make sense. How should it be defined? How should we define value? How should we define value? Somebody tell me, what is the value of a priority queue? If you pop all elements, they should come out in the same order, right? So 2 objects of priority have the same value if and only if there does not exist a distinguishing sequence among all the salient operations. You named only pop. What if I push and then pop? Okay, so it's a little worse than. Should such a class be regular? So, i.e., should the priority queue class support all of the value semantic syntax of a regular class? In other words, how expensive would operator double equals be to implement? And how would we figure that out? I mean, how on earth would you know whether 2 arbitrary priority queues could be distinguished in some way? So necessary, they have the same number of elements, the same number of respective element values. Sufficient, the underlying linear heap order is the same. That's certainly sufficient, but is it necessary or not? Here we have an example of 2 identical, in the sense of they have the same values, of course, and here we have 2 different underlying representations that pop in the same order, but there exist distinguishing sequences for them. Can we always do that? If we're not sure, should we try to do that? And what if we know that 99.9%, but not 100% of the time we can? And I say no. So I'm just about,
5 minutes.
I'm going to be done. Don't worry about it. Perhaps, okay, so perhaps we make it a named function, but suppose it were true that for any pair of priority queues, there did exist a way, a constructible way to tell the difference. And what would the complexity of operator double equal be? So suppose it were true that for any pair of priority queues where the linear heap order is not the same, there exists a sequence. All I need to do is check that the linear heap order is or isn't the same, and I can do that in linear time, right? I just walk the array. The trick is to prove that that's true. And if it is true, then it's O of n, and if it's not true, then who knows? And until quite recently, meaning about 2 years ago, I didn't know the answer. I had a conjecture. But finally, there is a very quick, simple proof, which I will put up, and almost no one will understand, but I'm going to put it up anyway. And suppose there's a highest index somewhere where the 2 differ, and you just look at that index, and you say, all right, what I'm going to do is I'm going to synthesize a distinguishing sequence by, I'm going to add a whole bunch of lower priority elements, and then I'm going to drop in a high priority one, and then I'm going to add a whole bunch of more low priority elements, and then I'm going to drop in a high priority one of a different value. So I have the same priority but different values. And if you look here, you'll see that they're going to come out in a different order. And without explaining this in the detail that I would like to, what's going to happen is I'm going to start popping, and after a while, they're going to be in different orders, and the top element is going to be a different value. So already I know they're not the same value, and then once I pop it, I've popped 2 different values. So this is a proof. It does work. But we're out of time, so I'm going quickly. So the idea is, yes, it should, because it's O of n, and it wasn't hard to write the code. It was hard to prove that's the right thing to do. So the conclusion is, takeaways. Some types naturally represent a value. Ideally, each type will have regular syntax. Moreover, all operations of value should follow proper value semantics. Values derived only from their own state. We want to adhere to the essential property of value. We want each object to behave as if it has a canonical internal representations. Two objects of a given value semantic type have the same value if there does not exist a distinguishing sequence among all of its salient operations. It's in the DNA of the object. If you have a value semantic type and you start deleting operations, it will continue to be value semantic even if it has no copy constructor, no assignment operator, no equality comparison operator. It's in the manipulators. The key takeaway is what makes a value type proper has essentially nothing to do with syntax. It has everything to do with semantics. A class that respects the essential property of value is value semantic, otherwise it's not. Here's some information, and that's the end.
Dr. John Lakos. John, thank you very much indeed.
Okay.
Thank you very much. We've got a little gift for yourself.
thank
Come on,
you.
do it properly one more time. Dr. John Lakos.